Hello everyone, my name is Hubert and welcome to Teach Me channel. Today we will be looking at GCSE Chemistry Reactivity series. Now, this is quite an important topic because it will form a basis of many other topics such as displacement reactions and things like that. I will throw in for you two types of reaction that you need to know. Metals with acid reactions and metals with water reactions, and I will use those reactions to explain reactivity series to you and how it all works. So, if that sounds daunting, don't worry about it. It's actually pretty straightforward concept. I will explain it all. Without further ado, let's get started. So, first of all, let's get started with those reactions. I think that's the best way to go about this. Okay, so first of all, we have example reaction of hydrochloric acid reacting with sodium to give us sodium chloride and hydrogen gas. Now, if we did that reaction in a test tube, we would get something like this. We would get sodium there with hydrochloric acid here. And because we're producing hydrogen, we would see actually a lot of bubbles. We would see a lot of bubbles. It will be fizzing and bubbling until all of that sodium is gone. Now, if we do similar type of reaction, very similar type of reaction, but if we react hydrochloric acid with zinc to give us zinc chloride, and again, hydrogen gas, we would see something that looks more like this. We would see zinc at the bottom of the tube with hydrochloric acid in the tube, same acid, same everything, and we would see much less bubbles. Why is that? Why is that we see much less bubbles if we react zinc than if we react sodium? Well, that will be explained by reactivity series. Now, before I move any further, let's just cover reactions of acids with metals. So the general formula for those reactions is acid plus metal will give you salt plus hydrogen. So that's how acid plus metal reactions work. Now, another type of reaction we will cover in order to get to reactivity series will be reactions of metals with water. So here we have an example. We have calcium reacting with water to give us calcium hydroxide plus hydrogen. So that's a reaction of metal with water. We just chuck calcium into water, pure calcium thrown into water will start fizzing and will give us this sort of reaction. Now, if we look at another example of iron plus water, nothing happens. Iron doesn't react away in water with such a reaction. I mean, yes, there is another reaction that it can go down, but iron does not react in such way with water like calcium does. So, what is happening? Why is that happening? Again, that is because of reactivity series. Now, I'm getting to that. I will just give you a formula for metals with water. So if we add water to metal, we will get metal hydroxide and we will get hydrogen. So that's the general formula. However, let's have what these two reactions have in common. What reactions of metals with acid have in common with reactions of metals with water? They both react, yes, they both fizz, but on a chemical level, what do they have in common? Well, what they have in common is that whenever metal reacts, in these type of reactions, in fact, in most cases, whenever metal reacts, it will give away electrons to form a positive ion and then bond ionically to a nonmetal. I mean, we covered different types of bondings and acids and the whole basics of acids, so check out my other videos if you are confused about what I'm talking about here. It's all on my channel, it's all there for you, so just check it out. And so, what do we have in common here? We have in common that metals give away electrons to form positive ions to begin ionic bonding. And why is that important? Because that is essentially what dictates reactivity series. Certain metals find it easier to give away those electrons than other metals. And those metals that find it easier to give away those electrons will be the most reactive ones. So sodium finds it way easier to give away those electrons, therefore this reaction happens much faster. And we see much more bubbling than, say, in zinc. Whereas in this example, it gets so extreme that whilst calcium is giving away those electrons and forming positive ions quite easily, then it can react with water directly. Whereas iron does not give away electrons and does not form positive ions quite as easily as calcium does. So iron, unfortunately, cannot react with water. So the ability of the metal to give away electrons in order to form an ion, positive ion, is what dictates the metal's reactivity and its position in reactivity series. So, moving on, that is reactivity series. That is essentially reactivity series that contains some of the commonly used metals. I mean, we could throw in all of the metals on periodic table, but this won't be necessary. These are the sort of ones you kind of need to know. So, that's reactivity series, and the higher we go in the reactivity series, the more reactive the metal is, and that will be very important for predictions, for making predictions as to whether reactions will happen, whether they will happen fast or slow. Say potassium would react faster than sodium with acid, and so we can tell which reactions will happen faster or slower, and in some other cases we can tell the limiting points. For example, with the reactions of metals with water, the zinc and iron and anything below zinc, essentially, and zinc included and anything below, won't really react with water directly. Whereas anything above, magnesium and upwards, will react with water. So we can predict the sort of limiting point as well as the rates of reactions using these reactivity series. Now, in red, we also have nonmetals. Now, these are technically not metals, of course. However, they are so often involved in metal reactions, and they are such good reference points that they are often included in reactivity series, especially when you get later on to displacement reactions and things as such. That actually comes in handy. Okay, so that's reactivity series. At the top we have most reactive, at the bottom we have least reactive. Now, if you wanted to remember these, I have two tricks. So I have two tricks to help you. remember this. Well, what do we have here? We have group 1 metals here. Right at the top we have group 1 metals, and then below them we have group 2 metals. So that's the first trick. Group 1 metals go above group 2 metals in this reactivity series. That's a good way to remember this. 1, 2, as you would count them, really. And group 3 actually goes here. So you literally count them 1, 2, 3. They go group wise. However, what happens within the groups? Within the groups, bar the transition metals, this may not necessarily work here in every single case. But with group 1 and 2, it's actually pretty predictable. The bigger ones, the bigger elements within the group are more reactive than the smaller elements within the group. And that's true for both group 1 and 2. And why is that? Why is that? Well, because the bigger elements tend to have more electron shells. Now, if we have a nucleus, right? Nucleus is positive, and then we have electron, which is negative. So, positive nucleus attracts electron. However, distance is important. The closer they are together, the more they attract each other. The further they are away from each other, the less of an effect, the less of an attraction they have on each other. So say if we throw in another electron shell with an electron here, the attraction will not be quite as much as here, because they are further away, and as physics states, the further away they are, the less attraction there will be. So now the bigger elements within the group will have more electron shells, and therefore electrons on the outer shell, the ones that are actually reacting, in potassium will have lower attraction to the nucleus than the ones in lithium, which are so much closer to the nucleus. Therefore, potassium will be able to lose those electrons easier, and because it will be able to lose electrons easier, it will be able to form positive ions easier. And same goes for group 2. So this is it for today, guys. I hope I helped you out, guys, here with these little tricks, how to remember the positions on reactivity series. And I hope this video helped you immensely. If you liked the video, give me a big old thumbs up. If you want to stay up to date on daily math, science, and biomedical science videos, hit that subscribe button below. And if you have any questions, give me a question in comments. I'm more than happy to answer. And thank you for watching. I really appreciate when you guys watch it. Thank you, and see you next time.